Good morning and welcome. Today we're going to use all this path integral technology that we developed in the past 3 lectures. We're going to use it in anger to actually quantize the scalar field. So the purpose of today's lecture is to illustrate to you how useful this path integral technology is and how efficient it is. So after today you'll see how you can, with far fewer moving parts, derive all the formulae you are familiar with from the quantization of the scalar field. So we should be able to pull it off in today's lecture, maybe a little bit of the next lecture. And after that, I hope you'll be convinced that this path integral is a very useful thing to know, if only to help you remember formulae. So the surface area of knowledge that you need to quantize fields with the path integral is much less than with canonical quantization. In fact, it's so amazingly efficient that people attempted to give it operational meaning and say that this is what quantum mechanics really is and what quantum field theory is. I don't hold with that. The message I like to give about the path integral is that it's a useful tool. You've got to know when to trust it and know when not to trust it. But for today, we can trust this tool. It's a fantastic tool. And we're going to see how incredibly efficient it is. So what's our goal? Our goal is to quantize the scalar field. We've done that already. We know how to do this via the canonical quantization procedure. But let's do it again, but using the path integral technology. All right, this should need no introduction. This is the action for the classical scalar field, the Klein-Gordon field. We're not going to do interactions just yet. Certainly by the next lecture we will. All right, so when you have a functional integral, when you quantize a classical theory with a path integral, you have 3 steps, right? You have to discretize, evaluate, and take the continuum limit. Because we only really can trust the path integral when we've got a finite number of non-relativistic degrees of freedom. So that's why we carry out step 1. Step 2 then becomes, as we'll see, a Gaussian integral, of which we are very well familiar with now. And then step 3, we take the continuum limit, because we will see that we have a lot of trivial divergences that come from if you take the continuum limit in the wrong way of this discrete thing. As long as you focus on operationally well-defined quantities, this continuum limit will exist. So as long as you follow these 3 steps, you're safe with a path integral. So we've got to do these 3 steps now for this very specific example of a scalar field in 4 dimensions, in 4 space-time dimensions. So to discretize, we're going to discretize in, and what I should say, I suppose, is discretization is an example of something that we're going to call more generally a cutoff. We're going to take all sets of infinite degrees of freedom and cut them off so we end up with a finite set of finite degrees of freedom. That's what discretization or cutoff, imposing a cutoff, means for us. Now we're going to put, to carry out 1, we're going to do 1 for the next half an hour or so. We need to discretize, we need to put the field on a lattice, and we need to also cut off what's called infrared divergences. Even if you put the field on a lattice, you still have an infinite number of degrees of freedom, right? Because the real number line goes from -infinity to infinity. So even if you put something on a lattice, there's still an infinite number of lattice points. So we've also got to compactify onto torus. So we're going to, why do I do that? Well, because you run into troubles when you have Gaussian integrals over an infinite number of variables. So there's no Gaussian measure for an infinite dimensional Hilbert space. So we take out, this is my little cartoon of, well, we're working in Minkowski space. This is my cartoon for Minkowski space. It's infinite flat Lorentz manifold. And we're going to take this continuous infinite flat Lorentz manifold and we're going to discretize it onto a torus, which means we identify this side with this side, this side with this side, and we want to identify, well, that one, this one, this side with this side, and so on. So we discretize everything onto a finite, well, latticelet. So this side is identified with this side, and that with that, and so on. N is a number, it's typically a very big number. So L is the size of our torus. We've taken our infinite flat space and compactified it onto this torus. And the size of our torus is, the side length is L. L, we want to be as big as possible, but still finite. So 10 to the 23 will do, but infinity won't. And then we discretize the interior of our lattice into n points, where n is given by L divided by, n to the 4 points, where n is given by L divided by epsilon. Epsilon is the lattice spacing between the lattice points. So four-dimensional pictures are hard to draw, so just think of the one-dimensional cartoon. So here's the real number line. And we discretize the real number line onto the circle. And we have sites all the way up to n minus 1 with lattice spacing epsilon. So we're just doing a four-dimensional version of this. That's fine. We've taken our space involving an infinite number of degrees of freedom and replaced it with a space where we only have a strictly finite number of degrees of freedom that we need to take care of. And in doing this, we're going to take our continuous field phi, defined everywhere in space-time, and replace it with a list of n to the 4 numbers. Where we just sample the field at lattice points xj. I believe that's correct. So another way of writing this is that each of these x's epsilon times by some j coordinate. Good, there we go. So we've taken we now reduced our problem to studying n to the 4 degrees of freedom. So at the current time, state-of-the-art Monte Carlo calculations with supercomputers, n is about 100. I think that's about right. So the latest calculations, they work in boxes of side about the proton radius. And they divide the proton radius up into about 100 points. So this is indeed how actual calculations are done with quantum field theory on the computer. So even when you have a box of side 100, that's really a lot of points. If you work it out, it's 100 times 100 times 100 times 100. And you can't do many of the calculations analytically. You're reduced to Monte Carlo sampling to estimate quantities. This is our set of discrete variables. There are okay, there's n to the 4 of these canonical position variables. Grows pretty fast. I mean, it grows polynomially with n, so I suppose that's something. Now, we also need, if we're going to discretize this integral up there, we need to do a couple more discretization steps. So one thing that appears throughout our calculations, of course, is the derivative of the field. I've already shown you how to discretize this guy. You approximate it by just the forward difference. Where E mu, oops. E mu is the unit vector in the mu direction. So as I emphasized in the previous lecture, this forward difference is not really the best way to do it, but you know, it's sort of good enough for government work. You would probably rather use a symmetric difference if you're going to do this on a computer, or even some higher order finite difference. But for this is fine. For our discussion, it's fine. And now, oh yeah, how do we discretize the integral? Well, you know, we discretize integrals with sums. Again, you could use some more higher order quadrature, but that's fine. I think you won't see any fundamental difference in the story. Now, we don't actually care about this finite lattice lit. In the end, we're going to take the limit that epsilon goes to 0. Right? We want to actually talk about our continuous field, but it is worth making these comments about the quality of these approximations here. You know, you should use higher order quadratures, you should use higher order finite differences, because very quickly we're going to run into field theories where we can't solve anything at all. There may not even be an easy perturbative limit to perturb around. This is non-perturbative quantum field theory. And then all of a sudden you really do care about how good these approximations are. So be aware that these are all things that you can change. You can change this if you want, you can change this to be a bit more accurate. And all those little powers of epsilon that you buy in doing that will improve your numerical results if you're going to do numerics. And to be clear, numerics are the only way we know at the moment to do non-perturbative calculations in general for quantum field theory. So there's no magical theory that can deal with non-perturbative quantum field theory as we know of yet. Now we have this in the path integral. Path integrals. So if you remember the path integral quantization recipe, it gives us these transition amplitudes as integrals of the action. Put a proportional sign like that. So we're almost done discretizing everything. There's one thing we haven't discretized yet. We haven't discretized this guy. Okay, but that's easy actually. That's we've got a finite number of canonical position variables. So we actually defined, this symbol isn't even, we don't discretize this symbol in this course. This symbol just stands for a corresponding integral finite measure for a bunch of degrees of freedom. So the way we define that measure when we have a finite number of degrees of freedom is just as the product over all the j's of our normal finite, of our normal integral measure for these position variables phi, or if you like, q's. N to the 4 integrals, right? It's just a big, long repeated integral. Good, so we have everything we need. Except, like, let's make our life a little easier. So we're doing everything in real space so far. And real space is fantastic for gauge theories on the computer, as we'll see. I guess I'll mention something about lattice gauge theory before the end of this course. But if you do know a better basis, then why not use it? It makes your life just so much easier. And we do know a better basis. Right? We know how to diagonalize the Hamiltonian for the Klein-Gordon field. We know how to find the canonical degrees of freedom, which are decoupled for this action. So there's no point in working in real space if there's a better representation available to you. You should use that unless there's a compelling reason not to use it. And so the space that we're going to use, of course, is Fourier space or momentum space, because that in the quantum world is the basis where the Hamiltonian is diagonal. So why are we doing this in real space anyway? So I'm doing it in real space so that you have the basis there for later discretizations when you don't know how to diagonalize the Hamiltonian. But for now we do, so let's finally admit it and go now to momentum space. All right, now we have a notation problem. Okay, first of all, I guess I've got to tell you what V is. V is the volume of our torus. Now we have ourselves a little notation problem. I don't want to put hats on Fourier variables here because hats are what I reserve for quantum fields, and this is definitely a classical field. I could use capital phi, but I guess I just don't like doing that. I think that it's reasonably unambiguous. That a K or L argument when we write the field as a function of K or L or maybe M, and I think we only need K or L, then that means it's actually the Fourier variable, the Fourier transform of our real space field. Because I don't, you know, if we go down the road of adding hats, then we're going to have hats and tildes and circles and yeah. So it's not worth it. let's just agree that if you write down phi of k, then you mean Fourier space, and if you write phi of x or y, then you mean real space. And this k of n, what is it? Well, it's just some 4 vector and n of mu is an integer in our box, and we have this momentum variable is bounded between minus pi and pi. So we hereby define phi of k, the Fourier transform of phi, by the standard Fourier series. And then, of course, what's going to happen, right? You have enough experience with these things now to see what's coming. Everything will decouple when we write things in terms of this basis. We'll just about decouple. Now these calculations can get very intricate. There can be many steps, many epsilons, many lattice points and things like this. I'm going to write down the main steps of the derivation. There'll be lots of intermediate exercises. They'll be of the form, just evaluate this exponential sum, which is something that you're used to. Or they'll be of the form of confirm this identity. So there won't be large conceptual steps that I miss out in the following, but there will be many derivations that I skip because they're just tedious and you know the answers, I hope, from your previous courses. All right, so warning number 1. Phi k is complex. Just look at how it's defined. So even if phi is real, then phi of k is complex. Phi of x is real, phi of k is complex. But we do have that phi of minus k equals phi star of k. And that comes from demanding that phi of x is real. So that's why we have that. All right. So our independent variables are the real parts of these phi of k's and the imaginary parts of these phi of k's. If it's complex, you have to deal with the fact that you have real and imaginary parts. But this condition here that phi of minus k equals phi star of k, that gives us a constraint, and we can solve for that constraint by demanding that the naught component of kn is always greater than 0. So our independent variables are the real parts and imaginary parts of phi, but only for those kn's where the time component is greater than 0. That solves this constraint here. And then our path integral measure, well, I guess it's worth saying that since the Fourier transform is a unitary change of variables, the Jacobian is 1, and our path integral measure is then just equal to the product of the real parts and imaginary parts of these phi n's and phi kn's. But not over all variables, of course, only over those where the time component is greater than 0. So that's like, this is an exercise for you to confirm the Jacobian is indeed 1. So we've got a path integral measure, we've discretized our action, but now we've got our lovely Fourier variables. Let's write our action in terms of the Fourier variables. Of course, that's why we introduce them, because everything gets really easy. So in terms of Fourier variables, our action is, I'll just write out the answer, you have to confirm this. Yeah. Okay, I did this on the train this morning. Took me about 10 minutes. It's a slightly tedious calculation, but there's nothing particularly tricky about it. You just have to remember this is an exercise, of course. Just remember that if you take the sum of e to the I, j, k from over n as j goes from 0 to n minus 1, that gives you a delta k. That's the only thing you really need to remember from this calculation, to do this calculation. I think that's correct. Wait on. Yeah, that's right. That's all you need to know. And then you'll be able to confirm that the action has this particular form there. But now we are in business, right? Because we've got an action that's now diagonal in terms of, or decoupled in terms of the independent variables. We have a measure, and it's going to be a Gaussian integral, what we get at the end. So let's go for it. There it is. That's our path integral for the Klein-Gordon field on the lattice lit. Yo, question? Is that a Kronecker delta? Yes, that's a Kronecker delta. Delta k. Yeah, it's not a Dirac delta function, that's for sure. It's a Kronecker delta. So k is a variable that runs from 0 to n minus 1. And so delta k means 1 if k is 0 and 0 otherwise. Yeah, it's not infinity or anything like that. It's just a good old-fashioned Kronecker delta. Oh, I see. Yeah. Okay, I could have made that. Yeah, I could have made that clearer, right? Of course, the traditional notation is that, right? And by proportional to, I mean actually equal to. Oh, no, I don't. Yeah, there needs to be a 2 pi in there as well. Cha. All right. Now it's correct. So let's just call this integral I naught. Now that's a Gaussian integral over a finite number of degrees of freedom. We know how to do those. And without further comment, I'll just write out the answer. That's what you get. Remember a Gaussian integral. Because this integral is already just a product of independent Gaussian integrals, then you get this I and this V and this pi, right? It's just a whole bunch of integrals, independent Gaussian integrals. So that's why we get this particular formula here. And there's something that's rather nice about that, and that is that it's also equal to the unrestricted product like that. So it simplifies quite nicely. Yeah. All right then. What's going to happen here? So V is a number, right? We chose our field to be defined in a box of side L. K is a number, M is a number. And what happens if we take the continuum limit of this thing here? What happens if we let V grow to infinity? Is all right? Are all things well and healthy here? Or could we anticipate problems with this particular quantity here? So K is bounded, yeah? K is some number in the inverse lattice. But what happens as V goes to infinity in this product here? Does this integral evaluate to something that gets smaller and smaller or bigger than bigger? Well, as your box gets bigger, this quantity gets bigger, it goes to infinity. So, are we disturbed by this? And the answer is no, because it's operationally, this thing has no meaning whatsoever. In fact, this path integral here is only proportional to this transition amplitude here. That's all you get from the path integral derivation is proportional to. And there's constants everywhere, right? So the quantity itself is not operationally well defined. So we don't have to get distressed yet that we've encountered an infinity as we take our box to be bigger and bigger. We do have a right to be distressed if when we write down an operationally well-defined quantity, a quantity that you can go and measure in the laboratory, and we make a prediction of the value of infinity for it. Yo, a question?
There's a question. There's no difference between these two factors under the square root, so why not just evaluate the square root?
There's no difference between these factors under the square root, so why evaluate things like this? Because I want to write this as an unrestricted product down here, and so this makes this apparently Baroque choice of notation is because it matches better with the continuum limit later on. So it's, yeah, I could have just written that as without the square root, but then a restricted product, but that's not what we want ultimately later. All right, so this quantity goes to infinity, but we don't have to be distressed yet, because we haven't written down an operationally well-defined quantity that goes to infinity. The minute we do that, we have a sick theory, and we have to throw it in the bin. This hasn't happened yet, though. Now, I'm going to give you, as I mentioned at the beginning of this lecture, the beauty of the path integral formalism. It gives you a very small surface area of knowledge that you need to remember, and I'm going to give you a heuristic way to remember this result. I'm a big fan of these heuristic methods because you can focus your energies on the conceptual details at a higher level before you finally dive into the actual technical details. So what's the heuristic way to remember this result? Well, one thing that you should remember from the previous lectures is that this Gaussian integral here evaluates to the inverse. So what I want to say, let's see. Yeah, the inverse square root of the determinant of A. This should be familiar to you by now. Now I want you to think about our Gaussian path integral. I'm going to put quote marks around it because this is not yet well defined what I'm about to say. Let's think about this. So that's what our, this is one very efficient way to write down the path integral for the Klein-Gordon field, is you just write down, you put the action in the exponent and you just write out the path integral like this. Now I tell you that you have to discretize, evaluate, take the continuum limit, but of course, the whole point of the path integral formalism is that at some point you gain practice in how you use it and you know when to trust the results and you just don't bother with the intermediate discretization steps. So I want to get you used to that. And so the idea is to think about this thing here. I want you to think about that as like a matrix exponent. So see, this integral in the exponent, in the action, if you think phi is to x, the vector x, what this Klein-Gordon operator is to A, then this thing here looks like a kind of continuous version of the expectation value of a matrix with respect to a vector. So this is sort of a more general thing. These kinds of expressions are like matrix expectation values like this. And if that's the case, and we're willing to take, some bold extrapolations, then we could have just straight out written out our functional integral without discretizing everything first. So I think the thing that characterizes physicists is that they're willing to boldly extrapolate. So let's do that. Let's behave like a physicist would. And so we believe then that the answer should be, well, if A is to the Klein-Gordon operator and x is to phi, then we know what the answer should be. It should be 1 over the square root of the determinant of minus delta squared minus m squared. That's what it should be. Whatever that might be. So it's worth appreciating this for a moment, because there's more than just a grain of truth to it. You can make sense of this thing, and we will make sense of this thing later in the course, just to a certain extent. And do you see how much knowledge we required to completely derive all this stuff on the previous boards? So as long as you remember that as long as you remember how to make sense of this, and we will, then we didn't have to do all this discretization stuff, blah, 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 blah. We could have just gone, okay, the action's quadratic, and that looks like this matrix expectation value thing, and I know how to do the Gaussian integral for a finite number of variables. Let's just boldly extrapolate to the continuum and write down the answer just by analogy. And it works. So you can do away with the first 30 minutes of this lecture and have just boldly extrapolated. That could have been the whole lecture there in this second half of that board. It's pretty amazing. Of course, what makes good physics is that you can't just boldly extrapolate everything. I mean, if you did, you'd believe in negative temperatures, for example. So you have to gain some intuition about when an extrapolation is correct, or when it's false, or when it's telling you about new physics. So that's why I'm going to drag you through the details of these discretizations a good number of times more until you've gained that intuition to be able to write down expressions like this confidently and say, I know that if I was to discretize everything, then it would come out fine. You got to first learn the changes and then forget them. Do the details. And then once you've done the details enough times, you will feel intuitively whether a result like this is to be trusted or not. And it might come down to, it might come down to a situation in your life where you really need a result to be correct because, you're making a prediction about the trajectory of a spacecraft. People's lives might depend on your calculations, in which point I would highly advise that you discretize everything and make sure your numbers are correct. Or it might come down to matching an experiment. You might have some theory about the phenomena that's being observed in an experiment, and you do the calculations heuristically like this, and you get results that match the experiment. Then I'd be inclined to say your results are also correct. There's a grain of truth to them. So as long as you know the context in which you're doing your calculations, you'll know whether or not to just trust bold extrapolations. If it's a spacecraft trajectory with some astronauts, do make sure you do all the details 3 times. But if you're trying to explain some physics in an experiment with a clean intuition, then you're much more free to use these kind of bold extrapolations, because there must be some grain of truth if you get the right answer. So, different contexts demand different levels of rigor. Now, so this quantity is as ill-defined as that quantity is up there. Right, the left-hand side is definitely infinite as v tends to infinity, and this thing here, well, you know, it's infinite, right? There's no sense that can be made to this thing here. But we know how to get rid of these harmless infinities, because that's not an operationally well-defined quantity. I naught actually cancels for operationally well-defined quantities, and I'm going to demonstrate that to you now by calculating something that really is measurable in practice, namely the two-point function. Okay, in the previous lecture, we learned a recipe for how to calculate the two-point function using path integrals, and it's this. Minus, plus, minus. That's how we can calculate a two-point or an n-point correlation function from a path integral. And this for me is like the formula for this course. Because if you combine it with the bold extrapolation here, then you get a really just such a quick and elegant derivation of the answer. It's such a fantastic formula. Yeah, so we're going to calculate it. We're going to first do it the hard way, though. You don't have the right to boldly extrapolate until you've done some hard work. So we do it. Amongst other things, well, in fact, we more or less only need this. We're going to need this product of the field operators. But remember, on the discretized world, these field operators are these Fourier sums. And so this becomes a not particularly elegant expression that you just have to live with. That's what it is. We just substitute in our Fourier sum. And we get this double sum over the Fourier modes. Yuck. Well, it's going to get a whole lot yuckier, I'm afraid. So let's call this star, I guess, the numerator Just to be consistent with what I've written here, I'll put L's. I've just replaced those N's with L's just to be consistent with the next line. And then you have these integrals. The real part, the imaginary part, and then we have, it doesn't get better. So you've got these phi's, right? Phi's are complex, so we have to write them in terms of the real and imaginary parts. Blah. So that's just the two phi operators now expanded out into the real and imaginary parts. Real, not phi operators, phi quantities. And then finally we can write our exponent, which we worked out before was this diagonal guy here, decoupled guy. Yep. Are there eyes missing? Thank you. Indeed, there are eyes missing. Yeah. Okay. So it's an absolute mess, but it's not a terrible mess. Now that you have some experience with Gaussian integrals, you can see lots of stuff cancels straight up. You can see that it's actually a relatively easy integral to do, because it's just a bunch of independent Gaussians multiplied by quadratic terms involving the independent variables. So actually it's not so bad. And in fact there's many more cancellations, of course. We don't have to do all four integrals there, because you can straight out see that two of them are 0. So the integrals involving the real part of this guy and the imaginary part of this guy, all those integrals are just straight out 0, because the integrand would be odd. Similarly, the imaginary part of this times the real part of this is also 0. So we actually only have two integrals to worry about. And furthermore, if m and l are different, then the integral is 0. So we've cut down the number of terms we have to deal with dramatically already. And we also know that if KL is equal to Km, the integral vanishes. The only term which doesn't vanish is when KL equals minus Km. So the only time we have to worry about the integral is when Km equals minus KL. Yeah, question?
Yes, isn't there an integral missing in the product?
Isn't there an integral missing in the product? Oh yes, thank you. So there's a nice little exercise to deal with the final remaining Gaussian integrals, and you do actually get quite a nice answer. This is what you get when you actually carry out those remaining Gaussian integrals here in this nasty expression. Definitely an exercise, but one that just relies on some bookkeeping and referring to lecture 2. There's no, the Wick's theorem of lecture 2. So, great. We've managed to do the numerator, and in fact, we've done the denominator already, so we're done. You all took an exam in quantum field theory. You all know what the answer is for the two-point function of the Klein-Gordon field. I'm pretty sure that everyone in this room has answered that question correctly. So you know what the answer's got to be. All right? And the trick to getting that answer is to note that we've seen this quantity before. This is I naught. So the numerator divided by the denominator is something extremely interesting. Minus I on V sum m e to the minus I k m x1 minus x2 all divided by m squared minus k m. M is an unfortunate choice. N. Now I use plus minus. Okay. All right. This should start to look extremely familiar. If we take the infinite volume continuum limit now, then we can replace this sum with an integral, and we end up with something that you should all know very well indeed. Yeah. Of course, this is the thing you know very well. You just have to put the plus signs in the right place. Then you get the propagator. Now, that's fantastic. Let's compare it with what we would have written down had we been willing to boldly extrapolate the continuum version. Okay. So CTS means continuous case. So if you had just written down the path integral and said, I trust the path integral, Feynman was a clever guy. So if you did that, you would be writing down some very interesting expressions indeed. So we know what the denominator is. We've done that already. So this is minus delta squared minus m squared to the minus a half. And the numerator, well, that looks very much like one of these two-point function type thingies that we know how to do Gaussian integrals for as well. And so if the matrix, if A is minus delta squared minus m squared, then the integral on the top is something like the matrix element of this matrix, of the inverse of this matrix. So JK, whatever that means, right? And in fact, or x1, x2, I think, to be absolutely precise. You know, we evaluate the matrix, the inverse of the matrix at arguments x1 and x2, whatever this could mean. But we give this a name, this thing. We call that dx1 minus x2. So the amount of surface area of data you need to remember now is the following. You need to remember that you should call your matrix A, and the inverse of the matrix you call D. And why should that be a believable statement that the inverse of this matrix is D? So now I recall, so if A is this, then A inverse is that. Now I should recall to you something we noticed about the Feynman propagator way back in the first course. If you take a matrix and multiply it by its inverse, what do you get? You get the identity, right? Now, if you think that your matrix is this operator here, minus delta squared minus m squared, then whatever you multiply it by, had better give you like the continuous version of the identity, right? And we know what that is. It's the delta function. So we should have that this is equal to delta xy 4. And indeed it is, right? You remember doing this calculation. So if A is the matrix, if A is the Klein-Gordon operator is the matrix, then the inverse is indeed the propagator. And that's how you can remember this formula here. I'm just going to write it out now at the top, if you're willing to just extrapolate from the discrete case. So I'll write it in. So the numerator here is that. And so we get that cancellation and we get the result that we knew we would get. So this analogy works extremely well between multivariable Gaussian integrals and continuous functional integrals. It works so well it'll carry us all the way through our course. We're never going to encounter a situation, well, we sort of are going to encounter one or two situations where it can't entirely be trusted, and that will actually be a situation which reveals new physics. And that's a good sign of a good tool. A good tool is one where when it breaks, then you know you're learning something new. But before we do that, we've got some other work to do. So the first bit of work we have to do before we get into new field theories that we haven't discussed yet is we have to just fully complete the story for the path integral. Can we get all of perturbative quantum field theory from the path integral? Or are there some steps which aren't yet well defined or unclear? So we're going to get there before, and I just want to mention before we do that, 3-point functions. We should talk about, I've only done the 2-point function here, but it's worth doing a couple of higher order functions just so you can see the role of Wick's theorem. Well, 3-point functions are 0 because the integrand is odd. 4-point functions are kind of interesting. So there you have a path integral expression for this. With this limit guy up the front. You substitute, so if you follow recipe 1, recipe that we have for evaluating path integrals, step 1 is to discretize everything, substitute, and then step 2 is to evaluate. So it's a real mess, like it does not get better. The integrand for the numerator contains 16 terms. Of course, nearly all of them cancel. Oh, sorry. M all the way up to, let's say, L or something. So this numerator contains these 16 terms defined in terms of these Fourier components. Most terms vanish. Now, after you do these, after you take track of all the things that vanish, then you're left with terms that involve, say, KL equals minus KM and KQ equals minus KP. And then how do you evaluate integrals with a quartic polynomial of the variables at the front? Well, we have this beautiful general formula called Wick's theorem. So we apply Wick's theorem in the form that we've learned in this course. And we take the limit that v tends to infinity. And of course, what do we get at the end? Well, we know what we get at the end. We've proved Wick's theorem for precisely this quantity in the previous course. And it's reassuring that we get the right answer, right? So we get exactly but I'll leave all these increasingly horrible details to you just to confirm that the path integral prescription gives precisely the same answer as the canonical quantization prescription for the case of the scalar field. Yeah, I do think it's worth doing this exercise because this is the inductive step right here. So the base case n is 2 is a special case. And then how to get the general result? Well, you need to know how to get from the case for n point function to n plus 2 point function. And this gives you the inductive step doing this example. So it's worth doing n is 2 and n is 4, because then you'll spot the pattern, inductively spot the pattern, and you'll know how to compute the correlation functions for arbitrary n. Well, I have about 15 minutes. Let's do all of perturbative quantum field theory in one board. And the path integral allows us to do that. It's just such an absurdly powerful tool. Yeah, let's do interacting quantum field theory. The path integral way. Our action now equals S naught plus some interaction for reasons that will become, I hope, clearer towards the end of this course. This is the only one that you need to worry about. The 5-4 interaction. And if we just follow Feynman, or we believe, or we're willing to extrapolate what we've seen here, then we can work out nice two-point functions for the full interacting theory. So we'll call that interaction term there S int. And how would we do this now? Well, lambda is meant to be small. Right? We're doing perturbative quantum field theory. And so if lambda is small, then we can expand this nice number here, this is just a number in the exponent, in the integrand here, as a power series in lambda. And furthermore, we even know that this will converge, right? For any given value of the arguments, it's a number, the exponential Taylor series converges. Could not be simpler. So I'll write the limit as dot, 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 dot. And then we do these Taylor series now. There's all numbers here in the integrand here. There's no quantum operators, there's no Dyson series, there's just numbers. But each of these terms, S int, S int squared, and so on, are just powers of this operator phi 4. So we get, you start substituting in and you start evaluating. And the same sort of stuff on the bottom. So you get this ghastly series of terms, and then of course to compute stuff to order lambda you have to cancel off the numerator and the denominator. But you might not be entirely convinced this reproduces what we did last semester, but the next line I hope does convince you. You see that each of these terms here are just integrals of time-ordered products of quantum field operators in the Heisenberg picture, because that comes from the formula that I probably erased. Well, it comes from this formula here, right? So each of the terms here, whatever they are, dot, 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 the terms are always going to look like integrals of powers of field operators. So all the terms in this infinite series here are always going to have the form of some integrals with some powers of lambda of the path integral of phi x1, phi x2, and then a bunch of other phi's e to the is naught. And those terms are always going to be integrals of time-ordered products of field operators in the Heisenberg picture. So this is the benefits of doing these things. But those are Feynman diagrams evaluated. And in fact, if you keep track of the rules, you'll see that you get one-to-one correspondence between the terms we derived last semester using canonical quantization and the terms you get from the path integral prescription here. So you get the same Feynman. You get the same terms in this Taylor series, and you get the same Feynman rules for what terms will appear in the series. So I think I just about did make good on my promise to derive all of interacting quantum field theory in one board. Not quite. I mean, there's obviously some combinatorics you've got to do here before you've calculated all the terms. But you do match term for term the parts of the Dyson series expansion that we got last semester, yeah. Which is not a given, right? I mean, this tool, can it be trusted? Well, we're gaining trust in it because it's proved itself in this first example. I think that's a great moment to stop the content for this lecture today. Where are we going next? Well, scalar field theory is all well and good, but nature gives us more than just bosons. Nature also gives us fermions. We need to do, if we want to use the powerful tool of path integration to do interacting quantum field theory with fermions, we're going to need to make sense of something, right? Because on the left-hand side of this formula up here, we have a quantum stuff that's fine. The quantum operators are all well defined for fermions. We know what to do for Dirac fermions. But what on earth is the right-hand side? So for the bosons, the right-hand side is an integral over all field configurations, all classical field configurations. So for fermions, if we were just to directly take those words and say them there, then we'd say something very interesting indeed. We'd say that a path integral for fermions is a sum over all field configurations of a classical fermion field, whatever that may be. So for the next lectures, we're going to try and make sense of the words classical fermion field. Turns out you can make sense of it, and is very beautiful mathematics indeed. Of course, before I do that, though, I want to say one more thing in the next lecture about functional derivatives so that you can remember all these formulas even better. But I think by next lecture we'll start talking about classical fermion fields. All right, but for now, I think we can stop. So thank you very much.